You might relate with me. Every time I start working on my side project, I have to use packages. Then I read their documentation. I find out they are also using other packages. If we go further, they might be dependent on others too. This always makes me think how we created layers on top of layers over the decades. In the world of computer science, this is called abstraction. Abstraction is a fundamental principle that involves hiding the complex implementation details of a system while exposing only the simplified interface. In this video, I want to go back and explore how we reached here and how each layer is dependent on another layer. At the very first level, it is all about physics. In 1947, three physicists, John Barden, Walter Brittain, and William Shockley, were working on a physics problem at Bell Labs, where they built the first working transistor. They even won Nobel Prize for this in 1956. A transistor has three parts: emitter, base, and collector. When you send a small electric current to base, a large current flows from emitter to collector. In simple terms, it is an electrically controlled switch. Now, you may interrupt me and say, hold on, we already had switches that could be controlled by electricity. And you would be right. We had things called relays. They were mechanical. They had a physical arm inside them that had to clunk back and forth, which works on the principle of electromagnetism. They were slow and had moving parts, which could wear out, so they were not reliable for large-scale use. We also had vacuum tubes, which let large current to pass from cathode to anode if a small current was passed to the grid. But they were big, fragile, and used to get extremely hot. So again, what was the big deal? If a transistor was just another switch, how did it change everything? It was not the function, but the form of the switch that made the difference. Now, we have the switch with no moving parts, and it's very reliable and so tiny that your processor contains billions of them. Since they are electrically controlled switches, the output of one transistor can be used as input for another transistor. In this way, we can send multiple transistors to work together, and we will get something called logic gates. Logic gates are the next layer where you do not have to think about physics behind the transistor and use them to implement the Boolean algebra. It is the algebra of true and false given by George Boole in mid-1800s. Boolean algebra has operations like logical AND, OR, NOT. A logical AND gate outputs true when all of its inputs are true. A logical OR gate outputs true when at least one of its input is true. And logical NOT gate just flips its input. If the input is true, it outputs false, and vice versa. These concepts were abstract until Claude Shannon looked at a circuit with mechanical switches. He noticed that two switches in series acted exactly like AND gate. Both had to be closed for the current to flow. And also, two switches in parallel acted exactly like OR gate. Either one can be closed to allow the current to flow. Similarly, let's see how each gate is made. First, AND gate. Instead of mechanical switches, we can use transistors, which act as a controllable switch for the electric signal. An electric signal to A turns on the first transistor. An electrical signal to B turns on the second transistor. Only when both A and B are on, the current flows to the output. If either A or B is off, the circuit is incomplete and Y remains off. Now, OR gate. Let's first replace the mechanical switch with transistor. An electrical signal to A turns on the first transistor. An electrical signal to B turns on the second transistor. The two transistors are placed in parallel, so current can flow through either path. If A is on, or if B is on, or if both A and B are on, the output Y becomes on. Y only stays off when both A and B are off. Now, NOT gate. First, let's replace the mechanical switch with transistor. When the input A is high, the transistor switches on and all the current passes through the path with no resistance, making the output low. When the input is off, the transistor remains off. Current has to go through the path with the load and the output is on. The modern system uses different circuits for implementing gates to make them more efficient and faster, but they are out of scope for this video. These implementations are enough to understand and to move to the next layer, where we will use these components together to make combinational and sequential circuit without thinking about how logic gates are implemented. Some other logic gates are NAND, NOR, XOR, XNOR. NAND is the inverted output of AND. Similarly, NOR is the inverted output of OR. XOR gives true if both inputs are different, and XNOR gives true if both inputs are same. Now, let's try to add two 1-bit numbers using these logic gates. First, let's see what we want. If you are familiar with binary addition, then you may know. So if you observe this, the result can be larger than 1 bit if both inputs are 1. So we need 2 bits to represent the result. We can name them sum bit and carry bit. Let the sum be the rightmost digit. And if you observe this carefully, carry is generated if both are 1. And if you remember, we already discussed, AND gate will give 1 as output if all its inputs are 1. So we can generate the carry bit by using AND gate. Now, if we look for the sum bit is generated if both inputs are different. So if you remember XOR gate, it has the same property, so we can use the XOR gate to generate sum bit. The design you just built is known as half adder in computer science, and it is the building block of every ALU. Now let's expand it a little bit. Since half adder is able to add just two 1-bit numbers, but while adding two binary numbers, we may run into a situation where we have to add carry along with 2 bits. So we need to add 3 bits together, and for that we need to design something called full adder. We need an adder which can be able to do following things. Again, we can observe carry bit is generated if at least 2 inputs are high, and sum bit is generated if there are odd number of high inputs. Now, the full adder can be constructed using 2 half adders and 1 OR gate. The first half adder, it gives intermediate sum and carry. The second half adder, it's an intermediate sum and the carry in. This gives the final sum output and another carry. The final carry out is obtained by ORing the carries from 2 half adders. Now, these full adders can be chained together to get a sum of binary numbers having more than 1 bits. Okay, so we make circuits that add numbers, but a computer doesn't just calculate, it also has to remember. So how do we make it store a simple 0 or 1? The simplest form of such storage is built from logic gates, arranged in a feedback loop. If you take 2 NOR gates and connect the output of each to one input of other, you create a basic latch. It has 2 inputs, set and reset. When you pulse set high, the output goes to 1 and it stays there even after set goes low. And when you set reset high, it goes to 0 and it stays. This is static memory. It holds the value as long as power is on. But a simple latch changes its output as soon as input changes, which can cause instability in a larger system. A clock is a regular electric signal that alternates between high and low at a fixed frequency. By gating the inputs of latch with this clock, we create a flip-flop. A flip-flop only samples its input at the instant the clock rises or falls, then holds the value until the next edge of the clock. This synchronizes the whole system. Flip-flops are the core of all sequential digital circuit. Group them into arrays and you will get registers. Arrange them in a larger grid, you will get memory. Decoders and multiplexers are used to read and write in a specific memory location, and a simple CPU is formed. Now, we need a way for the CPU to understand what we want it to do. Every CPU has a specific set of instructions it can execute, and using this instruction, we can create programs that CPU will run. These low-level instructions are known as machine code, long sequence of 1 and 0. Every CPU architecture has different set of instructions. A program written for one architecture doesn't work on another. Writing programs directly in machine code is extremely tedious and error-prone. So programmers created an abstraction layer called assembly language. Assembly represents machine code in a more human-readable form using mnemonics like move, store, add, and others. Although assembly made writing programs easier, it was still too low level for programmers. You still had to understand every details about CPU architecture. So developers tried to build an even higher level language. Early languages like Fortran, COBOL, and Algol. They were major steps forward, but they were often too specialized or too cumbersome. Some languages were great for math, but not good for system programming. Some were designed only for business purposes, and others never gained widespread attention.
We needed something efficient and flexible.
Something that could work close to hardware, but still feels like real programming language. That's where the C language comes in. C allowed programmers to write code that looked more like human logic and less like CPU instruction. The C compilers takes this code and translate it down to assembly or machine code for a specific architecture. C made writing programs easier while still giving developers control over memory and hardware. Now, imagine if you want to create some simple apps like calculators or note-taking apps that can interact with devices, memory, and CPU. Then, you must have to understand exactly how to communicate with every device, manage memory manually, and control the CPU directly. This will be a nightmare. This complexity was abstracted by operating system. The OS provides standard interface for hardware, so program doesn't need to know how each device physically works. The OS decides which programs run at what time. It allocates CPU time, switches between tasks, and it prevents one program interfering with another. The OS allocates memory, keeps track of which areas are in use, and handles virtual memory. Instead of dealing with raw disk sectors, programs work with files and directories. The OS organizes data, handles permission, cache data, and ensures reliability. Programs doesn't send raw electric signal to hardware. The OS uses device drivers that understand each device. The OS manages communication across the network through standard protocols. Programs just use sockets or networking APIs without dealing with packet construction or low-level protocols. Applications are not allowed to directly access the most hardware for safety and stability reasons. Instead, they make a system call which switches the CPU to kernel mode, where the OS has full privilege. The OS then performs requested action like reading a file, creating a process, or allocating memory, and then returns the result. Examples of some system calls are read, write, fork, exec, etc. But even with C, an operating system, writing programs was still complicated. Developers keeps repeating the same word, so higher level languages like Python, Java, JavaScript were created. This language had many low-level details like memory allocation, system call, CPU-specific behavior, so developers can focus on solving problems instead of managing hardware. Then, we add another layer, frameworks and libraries. These are collections of pre-written code that simplify even more complex tasks. Instead of writing everything from scratch, developers can use frameworks for building applications, websites, games, and machine learning models faster and more reliably. And finally, at the very top, we have applications. Everything we use, browsers, games, editors, are built on top of all these layers of abstraction. Applications don't worry about CPU instruction, memory addresses, or device drivers. They rely on the enormous stack of abstraction built over the decade to make programming easier and more powerful.